Good afternoon. Just picking up with what we have had with functions, and we started looking into operations between functions, which we will return to, but in the meantime. Okay, now we had last week, we've had various types of equations in two variables, and we had at the foundation was slope. Okay, we had like the point slope form of a linear equation as well as the slope intercept equation. But just sort of stepping back and looking at slope, at least in the context of functional notation. And this is in what we have in the guise of average rate of change of a function. And this is, again, just like the functional notation for what we have regarding slope. And for average rate of change of a function, okay, and we just kind of giving a bit of a formal introduction. And for the average rate of change of a function, now the function might be linear or it could be nonlinear, and cases of what we have had in dealing with slope have involved linear functions. And we have for the average rate of change of a function, okay, and we have by definition, okay, we have the average rate of change of a function and this function, okay, it could consist of different variables, but I'll just regard this as y is equal to f of x between 2 points okay, so you have x01, y01, and now the author gives this in the context of functional notation for the y. Okay, so like y01, we say that's going to be the function at the input x01. And where we have the second point, x of 2, y of 2, will be represented as x of 2, and where y of 2 we have the function whenever the input is at x2. And for the formula, okay, so we have like the slope, which we're going to perfectly preserve the concept. Now in the average rate of change, okay, you might have not just slope but slope with SCC, and what the SCC is in reference to, that's what is going to be regarded as the secant line. And this line is going to pass through the graph of the function at two specified points on the function's graph. And we have for the slope of the secant, okay, you still have change in y with respect to change in x. And just for the functional notation, okay, so for y of 2, okay, we have f of x of 2 we have minus f of x of 1 all over x of 2 minus x of 1, and again we still have that x of 1 and x of 2 cannot be equal to each other. And just for what we have in the case of taking examples of what we have regarding average rate of change, and we'll take like in the case of a nonlinear function, okay, and we'll say we have a quadratic function. And we'll say that we have f of x is equal to x squared minus 4. And you have this given. And say if you're looking at determining the average rate of change Okay, so if you're looking at the average rate of change, okay, first of all, okay, we'll say between x is equal to -2 and x is equal to 3. And we'll have, okay, also from the same starting point, let's say we have between x is equal to -2 and x is equal to 4. All right, so we're looking at average rates of change. Okay, let's say starting from x equals -2, and we have the final destination points in the first case at x equal to 3, and in the second case we have x is equal to 4. And what we can do in the case of establishing the foundation, okay, so we're going to have 3 points of interest, okay, where we have x at -2, x at 3, and also we have x equal to 4. Okay, so we are using this function. So we're trying to find out the y value whenever x is -2, also when x is 3, and also when x is equal to 4. Okay, and let's say that if we have at x is equal to -2, so we want to have that y is equal to f of -2, and for x squared minus 4, so we're taking the square of -2, and the square of -2 is going to be +4, and 4 minus 4, okay, is equal to 0. Okay, so we have a specified point. Okay, so whenever x is -2, the corresponding y value is at 0. And if I go out to x is equal to 3, and we have for y, okay, so you have y is equal to f of 3, and following through, so 3 in place, and x leads to 3 squared minus 4, and 3 squared is 9, take away 4, okay, and we have 5. Okay, so on the graph of y is equal to f of x is equal to x squared minus 4, included with the order pair -2, 0, we also have 3, 5. And we can go ahead and obtain the y value whenever x is at 4. So y is equal to f of 4. Okay. And so we have 4 squared, which is 16, and take away 4, and that is equal to 12. So we have, as a point, okay, we come out to 412. Right. And so looking at the average rates of change, yeah, all right, so between x equals -2 and x is equal to 3, or on a very similar note, okay, so we have going from -2, 0 to 3, 5. And looking for the average rate of change. Okay. So we have here for the average rate of change. Okay. So again, you have y of 2 minus y of 1, or f of x of 2 minus f of x of 1, and you have all over x of 2 minus x of 1. And so for what we have in terms of the average rate of change between x equals -2 and x equals 3, okay, so I have the coordinates already specified. Okay, so -2, 0, okay, we'll have this as the first set of x and y values. And for 3, 5, okay, there'll be x of 2, y of 2, okay, and already had the specific values, okay, for the x and the y values, or f of x of 2, f of x of 1 values. Okay, so for y of 2 minus y of 1, okay, so y of 2 is at 5. We have minus y of 1, which we have at 0. For x of 2 minus x of 1, x of 2 we have at 3. We have minus x of 1, which we have at -2. And we have 5 minus 0 is 5. And for x of 2 minus x of 1, okay, we have 3 minus -2, so that will transcend to 3 plus 2. And 5 over 5 is equal to 1. So between x equals -2 and x is equal to 3, okay, the average rate of change, or in this case the slope between those two immediate points, okay, comes out to 1. Okay. Now, for what we have in the case of the average rate of change between x is equal to -2 and x is equal to 4, okay, so again we have traveling from and past, okay, -2, 0, all the way out to where x is equal to 4, okay, where we have the corresponding y value is going to be at 12. Okay, so for the assignment of the values, okay, for the first and second x and y coordinates into the average rate of change formula, okay, so -2, 0, we can say we have x of 1, y of 1, and let 4, 12 represent the second set of x and y values. And just reapplying, okay, what we have for the average rate of change formula, okay, which is the slope formula in effect. And so we have for the change in y, okay, so you got your f of x of 2 or y of 2, okay, that is going to be at 12. And you got minus f of x of 1, which again is going to be in reference to y of 1, so again that is going to be at 0. And for the change in x, so you have x of 2 at 4, minus x of 1, which again is going to be at -2. Again, so you have change in y, okay, overall, okay, that is going to be 12, 4 minus -2, you have 4 plus 2, which is going to be 6. And it turns out that the slope is going to be different as we go out to 4 in comparison to when we had going out to x is equal to 3. And so we have the average rate of change in this case, okay, to land at 2. And now just to give you a bit of a visual in terms of the dynamics, okay, that will play out again. So this is the original function, okay, have f of x is equal to x squared minus 4. And just looking at, okay, a visual representation of what we have here. Okay, so for what we have in the case of the activity, okay, so here's a snapshot, and again, just for the graph, okay, so we have for this parabola in red, Again, this is in reference to y is equal to f of x is equal to x squared minus 4. And for the graphs that you see here, okay, the straight line, okay, you notice you have both of these graphs, okay, you have meeting the function at negative 2, 0, and for what we have going from x equals negative 2 to x equals 3, okay, you have this line that connects these 2 points, okay, so that is going to be that secant line going from x equals negative 2 out to and beyond x is equal to 3. And for this particular secant line, again, okay, the slope is equal to 1. And you have negative 2, 0, and 3, 5 as those points of intersection. Notice for the activity, you have like a 1-to-1 ratio here, like going up 1, right 1, up 1, right 1, and so on. Okay, and now for the other secant line connecting negative 2, 0 to 4, 12, okay, you have a steeper line. And for the slope of this line, this secant, okay, that is equal to 2. And again, you have like a 2-to-1 ratio, you have going up 2, right 1. So you have like going up 2, shifting out to the right 1. And so you have a different secant line. And for what we have here, if I were to start from this point and then venture out further to the right of the y-axis, say if I go out to x equal to 5, x equal to 10, okay, the average rate of change is going to increase continuously, okay, where you have the slope, okay, to be increasing and getting higher continuously. And let's say that for what we have in the case of determining average rate of change of a function, and let's say that we're looking at the average rate of change so let's say we have of y is equal to f of x is equal to x squared plus 2x. And we'll say that we have in the first case, we'll say we have between x equals 1 and x equals 5, and we'll keep the same starting point. We'll say we have in the second case, right? This time we'll have going between x equals 1 and x is equal to 9. Okay, so for just the next few moments, let's see what the average rates of change will be for f of x equals x squared plus 2x in the first instance between x equals 1 and x equals 5, and in the second instance where we have between x equals 1 and x equals 9. Okay, just for the average rate of change, if you're still looking at it, that's fine. But for the given function, okay, so we have a quadratic function, and this time we have with two variable terms, where we have that y or f of x is equal to x squared plus 2x, and we have 3 points of interest at x equals 1, x equals 5, and also x is equal to 9. And for the given function, okay, so if I'm looking at the determination of function values, and we have at x is equal to 1, okay, we have for the corresponding y value, okay, so that's going to be f of 1, and here we have 1 squared plus 2 times 1, so 1 squared is 1, 2 times 1 is 2, and 1 plus 2 is 3. Okay. And so we have, as a point on the graph of the function, okay, we have that 1, 3. At x is equal to 5, and we have that y is equal to f of 5, and for x squared plus 2x, okay, so we have 5 squared plus 2 times 5, 5 squared is 25, 2 times 5 is 10, 25 plus 10, okay, so this comes out to 35, and so we have for this point, okay, we have 5 and 35. As for our x is equal to 9, for the corresponding y value, okay, so we've got y is equal to f of 9. Okay, so for x squared, okay, this is 9 squared, 2x becomes 2 times 9. And 9 squared is 81, and added to 2 times 9, so we have 81 plus 18, so this will be 99. Okay, and so 3 points we have on the graph. Y is equal to x squared plus 2x. Okay, we have 1, 3, 5, 35, as well as 9, 99. Now regarding the average rate of change, okay, so you have between x equals 1 and x equals 5. And again, so you're just connecting the points 1, 3, and 5, 35. So we have, once again, in terms of the slope formula. Okay, so again we have 1, 3. And with this as our starting point, we'll have this as the first set of x and y terms. And the destination point x equals 5, okay, that will be the second set. So for the average rate of change, okay, on the graph of y equals x squared plus 2x between x equals 1 and x equals 5. No other points before or after or in between are of particular interest. Okay, so for what is essentially f of x of 2 minus f of x of 1 at y of 2 minus y of 1. Okay, we have the coordinates already specified. So we have 35 minus 3. And for x of 2 minus x of 1, so that's going to be 5 minus 1. So the overall change in y, okay, we have at 32. And the overall change in x we have at 4. And 32 over 4, okay, this comes out to 8. Okay, so you have still an integer value for the average rate of change, and it is not limited to just integers, and it could be like, you know, a fraction, like 7/2, let's say, but for this instance, okay, we have at 8, and between x equals 1 and x equals 9, and in terms of specified points, okay, so you're going from 1, 3 to 9, 99. And so just connecting those dots with a straight line, and the straight line's slope is going to be the secant slope. Okay. I can just paste this again. Okay, same formula, different x or different y values and different x of 2. All right, so before we had 35 minus 3 over 5 minus 1, and now we got 99 minus 3 all over 9 minus 1. So you have the change in y at 96 units, and the change in x we have at 8. And a 96 to 8 ratio, okay, that reduces to 12. Okay, so this line is going to be even steeper. Okay, we have the slope at 12 units in comparison to the other line, which we have at 8 units. And looking at what we have in terms of the dynamics, okay, between these items. Okay, so for the secant lines, again, this is just a section of the graph of the quadratic function. Okay, again, we have y is equal to f of x is equal to x squared plus 2x. And for the secant lines of interest, okay, so going from x equals 1 to x is equal to 5, so we're connecting 1, 3 and 5, 35. And for this particular secant line that goes through these 2 points, again, the slope is equal to 8. And just a little bit of history repeating itself along the lines of what was presented for f of x equals x squared minus 4. It's like the farther out you go to the right, from the starting point, the steeper the curve is going to be, and the higher the value of each subsequent secant slope is going to be. Okay, so this time going from 1, 3 to 9, 99, and we have for the slope again of the secant, okay, that is equal to 12. Okay, and again, if I were to venture out further, say to x equals 10, x equals 20, and so on, you would have a secant slope that would be substantially higher than 8 or 12. All right, and so these are cases of determining the average rate of change of a function, and it's kind of like almost like a flowery language version of just determining the slope. Okay, just kind of sort of the fancy functional notation involved. Okay, now I had mentioned that we would get back to operations between functions, and I had introduced, okay, just like cases of the sum, difference, product, and quotient functions, and I sort of bypassed mentioning domain, but we're going to look into this as well. And for the operations between functions, and there'll be more operations than just the 4, but we're just sort of staying with what we have had. Okay, so we've had f plus g of x. Again, this translates to the sum of f of x and g of x. And for the difference function, okay, so you have f minus g of x. So you have f of x minus g of x. And for the product function, again, we have f of x times g of x. And once again, for the quotient function, for f over g of x, okay, this is the quotient expression whenever we have f of x divided by g of x. And once again, just repeating. Okay, so for the sum, difference, and product functions, again, all of these are going to have the same domain. And the domain will be formed by combining the restrictions, if any, that are placed upon the functions involved, and those functions being f of x and g of x. Now for the quotient function, it could have the same domain, but it could have possibly a different domain. I will say that sort of tying in the concept of domain. And let's say that if we were to determine just the results of the sum, difference, product, and quotient functions and their domain. And we'll have just representing f of x and g of x. And for right now, okay, we'll just keep these as linear functions. Okay, so you have f of x, and let's say we have is equal to 3x plus 7. And g of x, okay, we have equal to 4x minus 8. Alright, so just setting things up here. So looking at, again, just specifying what the sum, difference, product, and quotient function results will be, specifically for what we have for f of x and g of x. And then we'll look into the domain. Okay, and alright, so just looking at what we have for the functions. Okay, so for f plus g of x, we have f of x plus g of x. And specifying, so f of x, we have at 3x plus 7. We got plus g of x. G of x, we have at 4x minus 8. Alright, so again, just use the parentheses just to denote the separation of what we have for f of x and g of x. And upon removal of the symbols, okay, so we're going to have no sign change. But upon combining like terms, for f plus g of x, given what we have for these functions, we've got 3x plus 4x, which will be 7x, and 7 minus 8, okay, that will be negative 1. Okay. Now for the difference between the functions, as opposed to the sum, alright, so you have 3x plus 7, and you got minus all of 4x minus 8. Alright, so upon removing the parentheses, okay, there's no negative or sign or subtraction in front of the 3x plus 7. So this will stay. However, with g of x, with 4x minus 8 representing it being subtracted, okay, so I have removing the parentheses changes the signs of everything. For g of x, so 4x becomes negative, and what was minus 8 translates to the addition of 8. Okay, so you got 3x minus 4x becomes negative x, and we got 7 plus 8, okay, which is going to be 15. And just given the right functions, I just want to mention, if you got like a sum function, the output could result as, like in this case, a difference binomial, and vice versa, like a difference function can translate to what's going to be addition, okay, in the follow through. Now for what we have in the case of, yes? Question?
I was just wondering, when you get those answers, you wouldn't want to, you don't set them to 0 and then solve for x
No.
in this, you just leave them like that?
Exactly. It's kind of like going back to just like in the early sections of chapter R, where you're just looking at combining terms together. Yeah, there's in other words, you're just looking at adding the functions, but you're not solving for an equation yet.
Okay, all right, thanks.
Mm-hmm. Now, okay, so still for what we have with f of x and g of x, okay, if we multiply together, okay, so we got 3x plus 7, and we have times the quantity of 4x minus 8. Okay, and again, just looking at foiling out. Okay, so just kind of looking at this from the FOIL perspective. Okay, so you got 3x times 4x. Okay, so you got 12x squared. Outside product is going to be a negative 24x. And you have 7 times 4x, which will be 28x. And 7 times negative 8 is a negative 56. And as we look at combining, okay, the middle two terms, okay, so we have for the product function result, okay, so this will be 12x squared, and negative 24x plus 28x, okay, becomes positive 4x, and we have minus 56. And for the quotient function, okay, you have f of x over g of x, and oftentimes, and this is going to be another case, just the substitution will take care of the result here. And f of x, we have 3x plus 7. G of x, we have 4x minus 8. And between 3x plus 7 and 4x minus 8, the greatest common factor is only going to be the number 1. So other than just the number 1, okay, there's no, or a constant, there's nothing in 3x plus 7 that's a factor of 4x minus 8, or the other way around. Okay, so just a substitution, that is the quotient function in simplest form. Okay. Now, regarding domain, okay, for f of x and g of x, okay, now both f of x and g of x are linear functions. Okay, so you don't have anything like a rational function, namely a fraction, where you're trying to avoid a zero denominator, nor is there an even root radical expression where you're trying to avoid having a negative within, say, the square root or whatever the even root happens to be. So for x in both of these, you can have x to be 0, a positive, or a negative, and still come out to a defined value. So f of x has no restrictions. And for g of x, that is also the same case. Also, no restriction. And because there's no restriction for f of x or g of x, guess what? There's going to be no restriction for the sum, difference, and product functions. Okay, because there's no because to be able to work with adding, subtracting, and multiplying throughout, okay, you had to be able to work with f of x and also be able to work with g of x. And guess what? There's nothing in x that is disallowed for f of x or g of x. Okay, so this will carry forth. Okay, so you'll have no restriction. And again, the sum, difference, and product functions will have the same domain. Okay, and for what we have in effect, okay, is that with the sum, difference, and product functions, again, we had the same domain. That's going to be the set of all real numbers throughout. Okay, and now with the quotient function, okay, possibly having a different domain in comparison to the domain of the other three functions. Okay, so we're going to have for the rational function, okay, there's going to be a restriction on this one, okay, because the bottom part of a fraction cannot be 0. Okay, so 4x minus 8 cannot be 0. So there is going to be a value in x, okay, that is going to be restricted. So 4x cannot be 8. And so it turns out that 2 is going to be excluded. And just kind of going back to interval notation. So there's only one value in x that'll be left out. Again, that is with the number 2. Okay. But what is allowed, okay, will be those values of x greater than 2, as well as those values of x less than 2. And once again, we have continuity at opposite ends, okay, out toward negative as well as positive infinity. Okay, so with the essentially with f of x and g of x as well as the sum, difference, and product functions, we have again all real numbers for the domain. But in the case of the quotient function, again, this is going to be the odd man out, for 2 is going to be excluded. And with the interval notation, okay, so you have values of x less than 2. Now, so we have those values of x which will be greater than 2. Okay. And once again, we have the use of parentheses throughout. Now, another situation where we have operations between functions, and this will be if you have specified inputs. And right now we've had for operations between functions, we maintain the general case of where the input essentially has been x all along. Well, let's say if you have numbers involved. Let's see, we'll call this operational functions with specified inputs. And with the sum difference product and quotient functions, okay, these will be, I think, fairly straightforward. And let's say if we have given, let's say we have 3 distinct functions. Let's say we have f of x is equal to 2x plus 3. And say we have g of x is equal to x plus 10. And we'll say we have h of x, okay, is equal to x minus 3. Okay, now for specified inputs, okay, let's say if you have if you were to determine, okay, say we have f plus g of 4, and we'll say we have f minus h of 7, and we'll say we have g times h of 5, and we'll also say we have h over f of negative 2. So we have just for the specified inputs, okay, so instead of just x, okay, we have numerical values. Okay, so for f plus g of 4, okay, just like f plus g of x branches out to f of x plus g of x, f plus g of 4, we can say that is f of 4 plus g of 4. Okay. And just looking at specifying what these values are going to be. Okay. So you've got f of 4, and with it 4 representing x, so I can just operate along the lines of f of x, but with x at 4. So for 2x plus 3, this will be 2 times 4 plus 3. 2 times 4 is 8, and 8 plus 3 is 11. As for evaluating g of 4, so we are referencing g of x, and where g of x equals x plus 10, well, we're going to have g of 4 is equal to 4 plus 10. And so that is equal to 14. Okay, and so I can just fill in the numerical values. So f of 4, again, it's going to be at 11. And g of 4, again, is going to be at 14. In this case, so we have 11 plus 14, so the output value for this sum function is going to end up at 25. All right, now for f minus h of 7. Okay, so you have like your f of x minus h of x, but with x at 7. So we're now looking at f of 7 minus h of 7. Okay, so looking at evaluating f of 7. Okay, so we have f of 7 is equal to 2 times 7 plus 3. 2 times 7 is 14. And 14 plus 3 is 17. And now for h of 7, okay, we're referencing h of x. H of 7 is going to be 7 minus 3. And 7 minus 3 is equal to 4. And so we have upon following through, okay, so we got f of 7. Okay, so we got 17. And we got minus h of 7. Okay, so h of 7 again is going to be at 4. And 17 minus 4 comes out to 13. All right. Now, for what we have in the case of g times h of 5, okay, and instead of multiplying out binomial expressions, okay, we're just going to multiply numbers. Okay, so you have g of 5 times h of 5. Now you could use the product of binomial expressions and just put in that one value 5 in for x in the general output. That's another pathway, but for g of 5, again, so you have g of 5, so that is going to be 5 plus 10. So it'll be 15. And for h of 5, again, so you have h of 5 is going to be 5 minus 3. And 5 minus 3 is equal to 2. And looking at attaining the product, okay, so we got g of 5 at 15. We got times h of 5, okay, which we have at 2. And 15 times 2 comes out to 30. Okay, and we have our h over f of negative 2. Okay, so this is going to be h of negative 2 all over f of negative 2. And for h of negative 2, okay, so we got negative 2 minus 3. So you have it negative 5. And for f of negative 2, again, so you have 2 times negative 2 plus 3. So you got negative 4 plus 3. Okay, and that's going to be a negative 1. And so, looking at what we have now and substituting, okay, so we got h of negative 2, okay, that's going to be at negative 5. And again, f of negative 2, okay, so that's going to be negative 1. Negative over negative is a positive, so we have negative 5 over negative 1 becomes 5. Okay, all right, now again, just looking at what we have concerning functions and domains, and I'll give you cases here. me see. Yeah, I'll go with this one. Okay, so we have given f of x is equal to x squared plus 1 and g of x is equal to x squared minus 4 and say if you were to determine f plus g of x, again, all four of these operations and their respective domains. Okay. All right. So just setting up what we have here. Okay, so you have f of x is equal to x squared plus 1. G of x, okay, is equal to x squared minus 4. What I had in mind. Okay, so for f plus g of x, okay, so we're looking at combining x squared plus 1 and x squared minus 4. Okay, and just removing the parentheses. Okay, so you have for this output, you got x squared plus x squared will make 2x squared, and 1 and negative 4 will come out to negative 3. All right, now for f minus g of x. Okay, so you got the difference between the same functions. Okay, and say just removing parentheses. So you got x squared plus 1. Now x squared minus 4 will have sign changes. So we have a negative x squared. Subtraction over minus 4 translates to addition. And here x squared minus x squared goes out. And we got 1 plus 4. And so this will be the constant value 5. And in the case of the product, okay, so you have x squared plus 1. All of that times all of x squared minus 4. And foiling out, okay, so about x squared times x squared, that will be x to the 4th. Now we'll go ahead and combine the outside and inside product, so we have negative 4x squared plus positive 1x squared. So we got minus 4 plus 1 is going to be negative 3. So you have x to the 4th minus 3x squared, and then we have minus 4. And for what we have in the case of the quotient function, Okay, so you have for f over g of x. And so this will ultimately translate, okay, where we have f of x at x squared plus 1 all over g of x, which will be at x squared minus 4. Okay, so those would be the results for these functions. Okay, now where the domain comes in, okay, now you got f of x and g of x. Okay, so both of these are going to be second order functions as opposed to linear. But like the linear, okay, you don't have an even root radical suggesting that the expression cannot be negative, nor do you have a fraction suggesting that any part of it cannot be 0. Okay, so you have a bit of history to repeat since you don't have restrictions for f of x or g of x. And this will carry forward to the sum, difference, and product functions. Okay, so f of x and g of x each will have no restriction. And this will roll over again to the sum, difference, and product functions. Okay, and for the sum, difference, and product function, again, there is no restriction. Any function or operative that has no restriction at all, we will have the domain again to be the set of all real numbers. And once again, the quotient function can be the odd man out, and it's going to be, because while you can work with f of x and g of x unconditionally for the sum, difference, and product functions, we have, however, with the quotient function that g of x cannot be 0. So there is that situation. Okay, so x squared minus 4 cannot be 0. And if that cannot be 0, then neither can the factors. And pinpointing what value or values of x will be excluded from the domain. Okay, so we have the x plus 2 cannot be 0. We have the x cannot be negative 2. And if x minus 2 cannot be 0, well, we're going to have the x cannot be equal to 2. Yes?
So, I see that it can't be equal to 0 or negative 2 and 2, but it also can't be equal to 0. You don't have to include that in the domain?
What I'm going to do is that for the domain, okay, I'm going to use the interval notation. And yeah, what I'm saying is that you're looking at what in x is going to be excluded from the domain. So you don't have to throw it. So you're not going to be throwing in the 0, but just the values that will cause x squared minus 4 to be 0. So you're leaving out just negative 2 and positive 2. Yeah, so we got for negative and positive 2. So those numbers will be left out. I'm going to show you a quick case too regarding domain without having to do the other stuff like determining the resulting operational function outputs. Okay, so we got here. Okay, so you want to have for f over g of x. we have for the domain, this will be broken up into 3 sections. We have between negative infinity and but not including -2. And we have for the middle section, so we're bypassing -2. Next set we have between but not including negative and +2. And the rest of the set will be those values of x that will be greater than 2. Okay. So again, we have the quotient function to be the odd man out. Okay, for we have not all real numbers for the domain, but all real numbers excluding negative and +2. All right, and just sort of kind of like providing a certain degree of separation between what we have among the operational functions. And say if you're looking at just domain, just the domain. So you had determined the domain. Of f of x, g of x, f plus g of x, all the way out to the quotient function. And say we have given that f of x is equal to 3 over x minus 4 and g of x is equal to x minus 7 all over x plus 1. Okay, so we have just starting out. Okay, so we have for f of x okay, so you have 3 over x minus 4. Okay, and just for the restriction for 3 over x minus 4, okay, now x minus 4 cannot be 0. So x cannot be -4. All right, now for g of x, okay, you have x minus 7 over x plus 1. Now,
I'm sorry, I have a question.
Yes.
It can't be -4 or it can't be...
Can't be +4, my bad. Yeah. I was reading it as x plus 4 for some reason. Okay, so we have for g of x, now x plus 1 cannot be 0. So you have x cannot be -1. All right. Now for the sum, difference, and product functions, and I'll throw in for the quotient function as well. Okay. For the sum, difference, and product functions, okay, I had to be able to work with f of x. So x cannot be 4. Even with the quotient function, I had to be able to work with f of x. So x still cannot be at 4. And also I had to be able to work with g of x. So x cannot be -1 either. And for what we have in the case of the domain, okay, for f of x, you're looking at all values of x except for 4. for g of x, you're looking at all real values x except for -1. Okay. Now the sum, difference, and product functions, we have the same domain. Okay, and just rank ordering. Okay, so we're looking at values of x less than -1, and we're bypassing -1. And guess what? We're also going to be bypassing 4. So you have another strip where we have values between but not including -1 and 4. And then we're going to bypass 4, and the rest of the set, okay, is going to be greater than 4. And so that statement in the interval notation will be the domain for the sum, difference, and product functions. Okay. And then we have with the quotient function. Okay. And we have for this remaining part. Okay, so we have for f over g of x. Okay. So this is going to be 3 over x minus 4. And we have over g of x, so we have x minus 7 over x plus 1. Again, got fractions. X cannot be 4 here. X cannot be -1 at the very bottom. And then clearing up this fraction of fractions. So you have 3 over x minus 4. And dividing by a fraction will be the same as multiplying by the fraction's reciprocal. So we have x plus 1 over x minus 7. And so we have for the resulting f over g of x. Guess what? Before I had in denominator position x minus 4 and x plus 1. But guess what? After the final dismount, so to speak, after taking the reciprocal of the bottom fraction, it turns out we now have what was x minus 7 in numerator position, and now it's been flipped over on its end, where we have x minus 7 also cannot be 0. So 7 is going to be left out. And so for the domain, okay, so just rank ordering, we still have -1 as the smallest value left out. And we have, along with -1 left out, again we have 4 left out, but instead of going past 4 on out to infinity, you now have 7, the exclusion of 7 as another roadblock. So you have this added interval section. Okay, so you got values of x less than -1, those between -1 and 4, but not including those values, and also you have between but excluding 4 and 7. And then we have for the rest, you have those values of x greater than 7. And the more specified exclusions you have, the more subintervals you'll likely have in the domain. And this quotient function happens to be a bit of history repeating. Okay.